Okay, guys, let's go over and review how to write equilibrium expressions and solve for the equilibrium constant first. Okay, so in any equilibrium problem, we're going to start with a chemical reaction. That's what's right here. Okay, and if you're having to solve for KEQ, they're going to give you some constants, or I'm sorry, some concentrations that you'll need to know. Okay, so first we need to write the equilibrium expression. We need to write what KEQ is. And KEQ is always going to be equal to the products, always in the square brackets that mean concentration, over the reactants. Okay? Remember that products are the stuff on the right of the arrow, and reactants are the stuff on the left. Okay? A little star of something to remember here is that solids and liquids are not included. Close enough. Okay, so if we're going to write it for this reaction, okay, KEQ equals the products, so carbon monoxide times hydrogen gas. Okay, they're both gases, so they must get included. There's no coefficients, so there's no exponents, over the reactants. Okay, carbon is a solid, okay, so it does not get included in the equilibrium expression. But water is a gas, so it does. Okay, and there's no coefficient, so we don't need to worry about exponents. That is our KEQ. Okay. Now, if we had to solve for KEQ, we're going to plug in these numbers into this equation that we just set up. So to do that, I'm going to switch over to red. Okay, and I'm going to go KEQ equals. Okay, we have CO with a concentration of 0.098. Okay, H2 with a concentration of 0.18 divided by H2O, which is 0.13. Okay, and then you just plug it into your calculator and solve. So we have 0.098 times 0.18 equals 0.01764 divided by 0.13. Okay, and we end up getting 0.13569. Since each of these numbers had 2 sig figs, we want to round our answer to 2 sig figs, so to that 3 right there. So it becomes 0.14. Okay, which means that our equilibrium favors the reactants. Okay, because KEQ is less than 1. Okay. So that's how you write the equilibrium expression, products over reactants. No coefficients, so it made our calculation really easy. You just plugged in the concentrations and plugged it into the calculator. Since KEQ is less than 1, it means that equilibrium favors the reactants. So there's going to be more of this stuff around at equilibrium. Okay, let's look at another problem. Okay, this one they gave it to us in a little different format. They gave us the concentrations in a table. Okay, but first let's go ahead and write our equilibrium expression. Okay, so KEQ equals products. That's the HI. Okay, this 2 comes down here and becomes an exponent. Okay, an exponent. Not a multiplying, an exponent. And now let me erase that because that's messy. make it prettier. Okay, so HI to the second power over our reactants, which is H2 and I2. No plus anywhere, it's just multiplying. Okay, this whole compound gets included. It's a gas, so that all checks out. Okay. Now, they gave us both the initial concentrations and the equilibrium concentrations. Since this is the equilibrium constant, okay, that's what KEQ is, we only care about the equilibrium constants. You don't even need to look at the initial concentrations. They don't really matter, okay? But we're going to use them to talk about a little bit of stuff, so I don't want to cross them out completely. Okay, they did 2 experiments. One where they started with just reactants, and one where they started with just products. And they found the concentrations at equilibrium. That's what's right over here. Okay, so let's go ahead and, oopsies, I erased something I didn't mean to erase. Okay, this is to the second power. Okay, let's go ahead and calculate KEQ for trial 1. So for this one right here, we're going to be focusing on these numbers, the equilibrium concentration. So we just plug them in to this equation. So KEQ equals the concentration of HI, 1.87, squared, okay, squared, divided by the concentration of H2, 0.066, times the concentration of I2, 1.07. Okay? And remember your order of operations, always do exponents first. Okay? So let's bring out the calculator. Clear it. 1.87 squared gives you 3.4969 divided by 0.066 times 1.07, okay, 0.0706. So 3.4969 divided by 0.0706 gives you an equilibrium constant of 49.5. Each of these ones had about 3, or minimum was 2 sig figs. So we're gonna round this up, and we're gonna keep it at 49.5. Okay, so we got a KEQ of 49.5, which means that since the KEQ is greater than 1, products are favored. Okay. Now, I've told you guys before that the equilibrium constant doesn't depend on initial concentrations. So let's go ahead and plug these numbers in and see if that's true. See if we get the same KEQ. Okay? This problem was taken out of your textbook. Okay? So let's find KEQ for trial 2. Now I'm going to plug these numbers into this equation. Okay? So KEQ equals 3.90 squared over 0.55 times 0.55. Okay. Calculator. 3.90 squared is 15.201, or 210, sorry, over 0.55 times 0.55, 0.3025, okay, clear, 15.210 divided by 0.30225 equals 50. Okay, so 59.5 and 50, that is just a rounding error. If we would have rounded this correctly, it would have rounded up to 50. Okay, so that checks out. Okay, that's how you solve KEQ. Now I want to go over some Le Chatelier's practice problems, okay? This guy, Le Chatelier. His principle says that if you stress or change a system at equilibrium, it will shift to relieve the stress. Okay, so let's look at some examples. Okay, what if we add table salt, NaCl? Okay, if the concentration of NaCl goes up, the reaction wants to get rid of it, so it's going to shift away from the NaCl. So it'll shift right. Okay, this is the right, this is the left. Okay, what about if pressure is increased? Okay, pressure is a weird one. Okay, pressure only affects gases. Okay, so if the pressure is increased, it's going to go toward the side with less gas. Okay, so let's go ahead and clean this up so we can analyze this one. Okay, on the left side of the equation, we have NaCl solid and H2O SO4 liquid, no gas, so 0 moles of gas. Where on this side, we have Na2SO4 solid and HCl, ooh, gas. Okay, so we have 1 mole of gas. So if the pressures increase, it'll shift toward the side with less gas, which is the left side. Okay. What if sulfuric acid, H2SO4, is removed? Okay, H2SO4 is right here in the equation. Okay, if you remove some of that, it's going to want to put it back. Okay, so it's going to want to shift left, okay, to try to put that sulfuric acid back. All right, time to clean it up again. Okay, the system is cooled, heat is removed. Okay, here's the heat. It's an exothermic reaction. And it's the same principle. If the heat's removed, the reaction is going to want to put the heat back. So it'll shift towards the heat, or to the right side. Okay. What if HCl is added? Here's HCl. If you add more of that, the reaction will want to get rid of it to fix and relieve that stress. So it'll shift left. Okay. Hopefully those problems helped you understand equilibrium constants and Le Chatelier's a little bit better.